Okay, so let me give you a little definition of complexity, diversity, and association. Um, First of all, association to me is kind of like memory. Okay, it's like saying, oh, this is kind of like with it's kind of like this, and it's kind of like this. Okay, complexity is different. Complexity is when you have interactions between things, variables, and the interactions are such that if one changes, then the others change. Okay, so that's pretty complex, all right, and very difficult to predict. And that is one of the problems that we have in understanding human thinking. Okay, so first of all, um, complexity is something that we have to deal with and control. And if there's any word that I would say describes what that process of thinking is all about, it's simplicity. We're always trying to simplify things, not trying to aggregate things. That seems to almost come natural because as you meander your way through this very complex universe that we live in, okay, it automatically tries to aggregate things. And once that happens, it becomes so complex, we run the risk of falling into chaos, which is very unpleasant. Let me also say that complexity is what makes the world interesting. Okay, imagine if the world were simply a monochromatic desert. Okay, completely flat. Okay, nothing is interacting and nothing is changing. Okay, that'd be a pretty bad place to live in. It'd be boring as hell. Um, so complexity does make our world interesting. Okay, now I want to talk about a couple of assumptions, and they are assumptions, not facts necessarily. But first assumption is we live in a universe that is becoming more complex. Um, Incidentally, at times I'll have to sit down because before I came here, I managed to get a gel injection in my knee from my orthopedist. So anyhow, um, okay, so the universe is becoming more complex. Okay, if our universe started out as a singularity, which was completely uniform, and of course we don't know what that really was, but since that expansion of that singularity, things have become more and more complex. Okay, all sorts of different chemical elements came out of it. Those chemical elements, and I don't want to get in trouble with Ed here, but that they started to aggregate to other chemical elements. Anyhow, we end up with look at this room. Okay, you realize how complex this is? So that's our universe is becoming more and more complex. Not only that, but when higher life forms emerged, we create more complexity. Okay, why? Because we keep looking for things, we keep exploring, and therefore our complexity becomes, it increases. Okay, so that's my second assumption, is that um, human life forms increase complexity. Third assumption is human thought is basically an attempt to organize the complexity of our universe. Okay. Um, it's hard to know necessarily what organization is, but that word, but at least I think we can use it and get some sense of what it means. Okay, so what is the local situation that we live in, right? I sort of refer to a philosopher, Bishop Berkeley, who said, well, there's no external reality. There isn't, okay? We create our external reality. Well, a lot of that's the old notion of if a tree falls in the forest and you weren't there, okay, it didn't fall. Well, I'm not a philosopher, but I don't necessarily I wouldn't want to be in the forest when a tree falls on me. So, but there's something interesting here because how do we perceive our external environment? Well, it comes to us in the form of energy, perhaps photons, acoustic waves, okay, and they have to be different. So we're taking that in all the time. Most of it we are not paying attention to. Okay, so for example, most of you um, were not aware of the particular light in this room. Okay. Hopefully, while you were listening to me, you weren't noticing that the shadow of the leaves were moving. Okay, because it's irrelevant to us. I'll talk about that a little later in terms of how we organize it. But basically, what we do is we organize energy inputs. Okay, and that way we make sense of our environment. It's not quite that simple because what we have to do is create cognitive models of our environment. Okay, I'll get into what cognitive models are in a little bit, but in order to understand that, I think it helps to understand some things about complexity science. So let me give you some of the concepts of complexity science. Okay, first one is self-organization. Okay, if you have a bunch of things that come together in some way, they seem to self-organize. Okay, the one that I've always has been kind of fun for me, when I start a class. Okay, everybody takes their seats, and I don't assign seats, and you all must have seen this in your classes. Okay, the second time they come, they all take the same seat. Why? Okay. Well, I don't know if I can get into the why yet, but that is self-organization. Okay. And it seems to be perhaps almost a property of our universe that when you have a lot of things, there is a tendency for them to self-organize. Let me show you, um, if I can, some other examples of that. Uh-oh, Ralph. Ah, penguins. Do you know what penguins do? They live in a pretty nasty place, okay, Antarctica. And actually, notice they're all facing in the same direction. Why? Was there a was there a master penguin who king, was an elected king and said, "All right, I want you guys to all face in this direction"? No. Okay. What happened is that there's very severe winds in the Arctic, in the Antarctic. So what's the best way to deal with that? Well, first thing you should do is huddle together. Okay. But if you're huddling together, then somebody's going to be facing the wind. All right. Not a good situation. Okay. So what happens is the people who are facing the wind say, "This is not good. I'm out of here." All right. So what do? They walk around to the back of the huddle, which leaves new penguins in the front. And they keep on doing this. So if we were able to look at this from above, you would see a moving group of penguins all moving into the wind. And then when they get up to the front, they peel off and walk to the back. Okay. Now, why do they? That's self-organization. There's nobody who told them to do that. Okay. It automatically occurs. Okay. I think it's pretty easy to see why they do that. It's more efficient. Okay. Um, so what's some other examples? Um, okay. One that's near and dear to my heart from my youth, cyclists in a race. Okay. If you are the front cyclist in that group, you are using 30% more effort. Okay. Well, if you're in a race and you're using 30% more effort, not good. You are going to just fall back. So what do? You get up, basically, you get up in front for 30 seconds, no, sometimes even less, and then you peel off to the back. Okay. Um, now, that, why would first of all, nobody could stay up front at any speed, even if they wanted to. But it also is fair. Okay, why shouldn't they peel off and go to the back? And then they slowly move up as each person um, peels off until they're back at the front again, and then they're back again. So once again, like we're not much different than penguins, are we? Okay, we have a dynamic situation of self-organization, and it occurs automatically. And you don't want to be a cyclist who stays up front. Another example of self-organization is, which one should I use? I think this one. Okay, a sailboat race. Notice they're all in the same direction. Okay, and there are rules to this. Okay, just like there are rules to a bike race. One of the rules is you better not be a leech. Don't stay in the back all the time, or you will get the displeasure, shall we say, of the people, of other guys in the race. Now, I don't want to get too much into bike racing because it's even much more complex than that when you have teams and the teams are jockeying. Okay, but basically whether it's teams that self-organize or whether it's individual cyclists, it's the same thing. So if we look at these boats, okay, they're all in the same direction. Okay, and they have rules. First, one rule is don't hit another boat. If you hit another boat, you're disqualified. Okay. So did that rule occur because of somebody who said, hey, one of the rules is don't hit another boat? Maybe, but we all know that. So it's going to occur naturally anyhow. So rules will generate out of self-organization. Okay. So that's the first concept of complexity science is self-organization. Second is called complex adaptive systems. Complex adaptive systems are where you have a whole bunch of different parts and they automatically adapt to each other. And it doesn't, once again, it doesn't require a king penguin or a king, a human king. Okay, what's some examples? Cities, New York City. Now we do have a mayor, but the mayor does not say, "Oh, we got to bring some food in for people." Okay, so he's going to go down to the local fruit market and say, "Please bring food in." Okay, no, it's going to happen naturally because they need food. Okay. And then what's going to happen is we have to get rid of the waste in the city. And there's all sorts of things that are going on in cities where it adapts. It's a system that adapts. The human body is a system that adapts. Okay. If you exercise, what does your heart do? It speeds up. What does your respiration do? Okay. If you start breathing faster and deeper. Okay. What else? Sweating. You start to sweat. And then when you stop, what does your body do? It sort of says, okay, I quit now. All right. And everything goes back to the way it was, whatever that particular situation was. The one that I always enjoy is seeing airports, being in an airport. Okay, so you never watch. There's always things moving around. There's fuel trucks going. They're putting back. How does that all work? Okay, they're putting baggage in, they're putting baggage out. The tower is talking to the pilots. Okay, and planes are landing. Think of how complex that is, and yet it keeps on going like that, without anybody. Yes, there probably is somebody who's the head of the airport, but he's not behind the scenes organizing all of that. Okay, another concept that you've seen, which is kind of like self-organization, is flocking. Flocking, if you've ever watched birds migrate, okay, what do? The geese, you've seen Canada geese, they form a V. Um, why do they form a V? Um, I think it probably has something to do with the aerodynamics of following another goose is easier. Okay, but not being a goose, I don't know for sure. Okay, but not only do that notice also the geese are as smart as us humans in a bike race because they don't stay up there. Okay, if you watch the V's, sometimes they break apart, then they come together, but there is no one goose that leads the other geese all the way from Connecticut down to someplace in South America. Okay, so flocking is again something that automatically occurs. Another concept is emergence. Emergence is sort of when something unexpected happens and it multiplies exponentially into something that you didn't really expect. Now, the classic example of that, which I hate, is the butterfly effect. Okay, the butterfly effect says there's a butterfly someplace in an Amazonian jungle, and he flapped his wings. Okay, and then it's with that flapping wings initiated something and initiated something, and next thing you know, we have a hurricane that devastates the Caribbean. Okay, well, yeah, but I sort of wonder. I'm trying to picture in my mind lining up, thousands of butterflies and getting them to flap their wings. Okay. And would that cause a hurricane? I don't think so. Okay. So the concept is interesting. Okay. But it really doesn't happen that way. And one of the problems is if you had the hurricane, would you be able to trace this back to the particular butterfly and the particular flap of that wing, okay, that started the hurricane? No, can't do that. Okay, so it's an interesting concept. Um, Also, I guess with butterflies, yeah, I um, must be must be pretty egotistical for a butterfly to say, "It was me. I did that." Okay, so no, that's not going to happen. We see emergence in all sorts of things. Okay, um, and it produces unexpected, unpredicted results. Okay, another is that there was a young man in, I guess, a couple of thousand years ago in a small Israeli province called Judea. Okay, and he decided he would go off preaching. Okay, and Jesus, okay, think of that as an emergent phenomenon. Look how it happened. Now, notice that it really, for there to be an emergent phenomenon, it has to interact with all sorts of other things. So remember what I said about interactions, okay? That's what complexity is, okay? It's oftentimes very hard to predict because we have a little change in what a gentleman says, a young man says in Judea many thousands of years ago, and yet it interacts with all sorts of other things, including the Emperor Constantine's mother, and we could go on and try to trace that back. So that's emergence. Another concept is scale. Um, Scale is depending upon how large or heavy things are, it makes a big difference. Okay, so if a butterfly lands on your head, you'd say, okay, not a problem. However, if an elephant stomps on your head, Okay, that's a problem. Okay, and that's a difference in scale. Um, I'll talk about, you're going to have to learn about some things about the principles of flight and airplanes. Okay. But do you realize humans developed an ability to fly in 1903? And that was, of course, the Wright brothers. Okay. What else? There were lots of things that flew before us. Okay. Insects. Insects have been flying for millennia. Okay. Birds have been flying for millennia. So we're kind of the latecomers. One of the problems with that goes back to scale. Okay. It's hard to lift heavy objects like people, like us, off of what we're standing on because gravity keeps pulling us to the center of the earth. Okay. It's what's called a point attractor. Okay. Well, it's much easier for insects because they don't weigh very much. Okay. So they developed that long before us. Last one I'll talk about is called salience. Salience is when um, we put extra importance on some object or variable. Okay, perhaps more than it deserves. And I'll talk about salience in terms of cognition. It often leads us into cognitive errors. Okay, so I've given you some short introduction to complexity science. Okay, now let me go back into cognitive models. Okay, what are they? They are basically internal representations of our outside universe. That's all. Okay. We hope that they are accurate representations, and sometimes they're not. Oftentimes they're not. And basically, what a cognitive model does is it coordinates the release of energy with the demands of our environment. Okay. Now that's pretty abstract, but if you think about it, we take in energy and we are going to use energy. Well, we don't just randomly use energy. Okay. If I just started walking around and going like this, I'm using a good bit of energy. Okay. But it's not coordinated with my environment. However, if I turn to Jane and I say, oh, Jane, did you know now I'm expelling some verbal energy? Okay. And it's in coordination with the social demands of my environment. So that's really important. And that's something that cognitive models do. Now, problem is environments, whether they're local, okay, or more distal, they can be overwhelming. In other words, we can take in a huge amount of these, I guess, energy differences. Incidentally, there always have to be differences. If you are staring at if the energy forms in terms of photons, in terms of acoustic waves, if there's no difference in them, if they don't vary, then we actually, our neurological system sort of wipes them out. Okay, so we're always paying attention to differences, and that's what cognitive models have to do. Now, that's hard because we need to maintain some stability and some balance in terms of cognitive models. And so without letting our environment overwhelm us. Okay. And I would have to say, what's overwhelm us? It's chaos. Okay. It's when we don't know what the hell's going on. Okay. And maybe that balance of coordinating energy releases with energy coming in gets out of whack. Okay, but the main thing I want to get across is all of the inputs that we get to form that inner representation is it's overwhelming. So how do we deal with that? And I guess what I thought was my contribution when I ended up writing this thing, okay, was, oh, there has to be some way in which we simplify things. Now, simplify? Yeah, okay, I never thought about cognition is a process of simplification. Okay. Before I pat myself on the back for that, um, I was doing some reading a couple of nights ago and I came across this quote: simplicity is the ultimate sophistication. Okay. Leonardo da Vinci. Okay. So he beat me to it. Okay. Although I have to say, I'm glad I'm in good company. It's not bad to be with Leonardo. Okay, so basically, cognitive models allow us to minimize variables, objects, things, whatever you want to call them. And here's the important part. We have to minimize their interactions. Okay, let me see if I can, let me get to this slide. Okay, here's a sort of a graphic model of interactions. Okay, and this incidentally comes from the work of Stuart Kaufman, who was an um, early researcher into complexity science, and he basically said, well, there are two. I'll identify two factors. One he called P, okay, little p, and that is something that is either you take it in or you don't. Okay, it's almost like a correlation. Okay, it's zero. If it's zero, it doesn't matter. Okay, um, the and however, the other part is what he calls K, and K is an interaction where if you change one thing, it changes everything. That's really hard to keep track of. Okay, now K equals 2 is not too difficult. Okay, we got three things, and we change one, it can change two others. Look at K equals 4. Okay, how on earth do you try to understand the interactions if I change I can't. Okay, if I change one of those and all the rest change, and we don't know how much they change, and some of them will change, maybe some of them will change in the opposite direction, that's really, really complex. Okay, so we can't handle that. Now, maybe we can handle K equals 4, but by the time you get to K equals 5 and K equals 6, because this is um, an exponential interaction, okay, it becomes too complex. So we are always minimizing, and the central task for a cognitive model is to simplify things so we avoid chaos. Okay. Now let me see if I can give you an example of this. Okay, you're in a kayak going down the Farmington River. Okay, and it's a nice day. And as you're going down, there are things that come into your visual field. One is trees on the bank. Are they important? No. So they don't interact. They are not K. They are P. And if we can just ignore them, in other words, they don't have any relationship to us safely going down the Farmington River and happily arriving at our destination. Okay. However, we could almost, as I said, we could put that into a correlation where, in this case, the correlation is 0. Okay. Now, what are the K factors? Okay, we're going down the river. Okay, there's a current to the river. Okay, that's important. Okay, as we go down further, there are rocks in front of us. Okay, some of the rocks stick out. Some of them are what we call pillow rocks, where they just go over and they're hard to see. Notice that also the current changes around the rocks. Also, you the position of the kayak is rather important. You don't want to go down the Farmington River sideways in a kayak, okay? Now, what happens is you're going along and you're keeping track of all of this, okay? Now you hit a place called Satan's Kingdom, where the currents are going all over the place, okay? You have a paddle, you're trying to cope with that, okay? And then there are rocks, and the rocks are coming at you fast. The current is changing. You hit a rock, it bounces, kayak bounces this way. Okay, you can't keep track of all of that, okay? So what you do keep track of is the total energy of the kayak in relation to the river, okay? And that's easier. I say, then you don't even have to necessarily, you don't sit there, oh, there's a rock, oh, the current switching. No, you can't do that, okay? Instead, you just have a sense of the river. And I guess people who do whitewater kayaking would call it a river sense, okay? I'll show you how that changes, okay? But what we're trying to do is avoid confusion. At first, as we hit Satan's kingdom and we're not keeping track of it, okay, we get confused, okay? Next, we get kind of a cognitive disintegration, okay? Next, it gets emotional, okay? Very emotional. And then finally, we might end up in a panic state. Once you get to a panic state, that's kind of a K=1 because you don't think of anything else. Okay, it wipes out cognition. Emotions do that. And if you don't get out of that state, well, what's going to happen is you're going to flip. Okay, flipping is not good going through Satan's kingdom because now your head is the keel for your kayak. Okay, and certainly there are two problems there. One is you tend to bounce your head off the rocks at the bottom of the river. The other is even worse. You don't have gills, so you can't breathe if you're upside down, okay? So we are programmed to avoid chaos, okay? Most of the time, we just don't like it. There was a study I did with one of my colleagues, Bill Neese. Okay, and we said, let's see if we can create chaos. Okay, so what we did was we got a bunch of students and we said, here's a problem. There's 3 cars, okay, and the cars are going to leave the same spot, okay, and they're going to go and end up at the same place. However, each car is going to have a different path. There's a percentage of that car running into a state trooper. Okay, there's speed limits. We made it so complex. And we said, which one got there first? Okay, and it was so complex, nobody could figure that out. Maybe if you put it in some kind of computer program, okay, but it was impossible. Okay, and we thought, oh, they were going to say this. Nobody can solve this. No, they each said, oh, it's this car. Another person would say, oh, it's this car. Well, are you sure of that? Oh, yeah, yeah. Oh, well, you know what? We asked you to do that after only 10 seconds. Let's give you like 5 minutes. You want to think about it. And they said, okay, all right, 5 minutes, didn't matter. They stuck with the same answer, okay? And it was their way of avoiding chaos, okay? We then did the same thing with a bunch of our psychology graduate students. We said, here's a problem, okay? And we gave them sort of different different symptomatologies, and we said, come out with a diagnosis. They all were, once they came out with a diagnosis, they were very sure of it, okay? There was a study that I've never been able to find a reference to it, but I do remember it very well. And what this person did was he was concerned because we psychologists don't agree with each other. Okay, you give us a problem. Okay, we just don't okay, which basically says that inter-judge agreement is very poor in psychology. It doesn't matter whether you're doing testing, psychological testing. So we said, okay, this person said, what is this all about? Is it just that we psychologists are so bad? So what he did was he got some gastroenterologists, he got some cardiologists, and gave them information. When incidentally, the amount of agreement for psychologists is a correlation, they correlate 0.4. Okay, 0.4 is not very good. And if you know anything about statistics, you square that and it gives you the percent of agreement, and that comes out to 16%. Okay, so we psychologists agree with each other about 16%. Okay, well, what about now we go to doctors? That's, come on, this is serious stuff here. Okay, we gave them these protocols. Okay, and the guy who did this study, they came out with a correlation of 0.4. They agree with each other 16%. They did it with bankers in terms of whether we should give people loans. Okay, guess what? 0.4, an agreement, interjudge agreement of 16%. Okay. The only thing, there were two things he put at the end of the article that I remember. One was, this seems to be a factor of complex judgment. Okay, and we don't like chaos. Okay, if you go to and the other was food for thought. Next time you go to see your primary physician, okay, that you go to see another primary physician, they may not come out with the same diagnosis. Hopefully they'll be close. Okay, so complex human judgment, when things get more and more complex, even if we don't know the correct answers, okay, we will assume we do to avoid chaos, all right, because chaos is so unpleasant. Okay, okay, what else do I want to say on this? Okay, one of the things that we do is, and this goes under salience, how we make certain things more important. I'm always amazed at the discussion about the great Civil War general Ulysses Grant. Okay, he was a great general. Okay, he also, at one point in his life, had slaves. Okay, well, how do you, these two things seem to be, that's not so good. How do we put them together? Well, you don't. Okay, people will be salient about, oh my God, he was a terrible person because he had slaves. Yeah, okay, and then thankfully he was a wonderful general. Okay, and through his campaign in the Mississippi, he basically won the Civil War for us. Okay, well, that's really good. It's hard to live with that ambiguity, and so we tend to make one more important than the other. Okay, so I'll stop there about in terms of, I don't want to get into political kinds of things. Okay, okay, another concept that I haven't mentioned, which it's an old I use it as an old psychoanalytic term called canalization. Okay, canalization, canal. If you're in a canal, you can only go one direction or the other direction. You can't go sideways. Okay, so that's sort of what it's about. Okay, well, as someone who's done a lot of sailing in my life, I kind of study sailing and different cultures. Well, it turns out that different cultures developed different kinds of boats. And once they developed their kind of boat, they didn't change. Okay, it was like cognitively they were in a canal and they could not change it. The Arabic civilizations on the eastern coast of Africa sailed across to the Spice Islands in India and Sri Lanka, Indonesia. They've been doing this for at least 1,500, 2,000 years. They built their boats by, they would have a frame, and then how did they put, you can't just have a frame, you got to have planks. They tied the planks onto the frames, and they tied the frames together with cord. Okay. Oh my God, I don't want to sail a boat that's held together with with wrapping tape or something. Didn't matter. They could sail across the entire Indian Ocean that way and back. Okay. Um, the Iroquois, and I'm sure other Native Americans, you know how they built their birchbark canoes? They didn't start with frames. They started by sewing together pieces of bark. Okay. And they'd have a big piece of bark, and then they would put a frame, kind of, but not a frame that was going to go in the boat. It was sort of like you now had this, this sort of I don't know what you'd call it, a sagging kind of piece of birch bark. Okay. And then they would start putting in the frames. Okay. And birch bark canoes not only lasted very long, but they certainly were efficient. Okay. Um, we European Americans, what did we do? Oh, we basically did what the Arabs did, except we weren't going to have boats going across the Atlantic and the Pacific to hold together with cord. Okay. So we would drill a hole in between the plank and the frame, and we knock a round dowel in there. Okay. And then we let it swell up, and it held it together. Now, of course, later on we started using screws, okay, because that was a lot easier. What about the Chinese? Okay, the Chinese built boats as it just like it was a piece of bamboo. They built their boats in sections, okay, with watertight sections all over, just like a piece it exists in a piece of bamboo. And then, of course, the culture that were the greatest mariners, the Polynesians and the Melanesians. What did they do? Completely different. They used two hulls together. They used catamarans, okay? And they settled the entire thousands and thousands of islands of miles in the Pacific Ocean, okay, with catamarans. And once these cultures found this is a good way, they couldn't change. And there's an interesting, I got to check on time. There's an interesting anecdote about Captain Cook, the British mariner, when he saw the Polynesian canoes, he thought, oh God, these are terrible. Okay. And no, they work perfectly fine. So, okay, that's the way cognitive models work. And once you develop a cognitive model, it will change because the environment changes. But basically, you try to keep stability in the cognitive model. Okay, now, the next part I want to get into, and how much time do I have left? Okay, all right. I want to use the Wright brothers as an example. How do we solve um, complex scientific problems? Okay, well, this is difficult. Okay, let me. What they are trying to do. These are the variables that exist in terms of keeping an airplane in the air. Incidentally, what is where is it? What is an airplane? You think about it. An airplane is a controllable wind generator, okay, that exists in a chaotic fluid, okay, and it also goes up, okay. Our atmosphere, think about it, it's not a stable thing. Think about it as a boiling pot, okay? So that's basically, it doesn't matter whether you're in a jet plane, whether you're in a propeller plane, okay? You're basically flying in a wind generator. And that wind generator pushes, if it's pushing air this way, the fan has to go the other way, okay? So how did they, now in a chaotic fluid, how did the Wright brothers solve this? Well, first of all, and I'll show you. This is the matrix they were dealing with. Okay, that is a k equals, I don't know, 15. Okay, it should have been not should have been insolvable. Okay? You can't solve that. Okay, well, remember simplification. How do you simplify something like that? Okay, here's how they did it. Okay, and these are sort of the 1, 2, 3, 4, 5, 6, 7 principles of how you solve complex scientific problems. The first is you detect underlying identities. In other words, some of these are kind of the same. Okay, for example, does it wind speed is the same as an airplane, a glider? Whether I keep it aloft by blowing air or whether I go like this, it's the same thing. Okay, it looks different, but it's an identity. Okay. Another that looks different is the relationship between lift, keeping this up in the air, and weight. Lift has to equal weight. Okay. Well, they seem like they're different. No, they are underlying identities. All right. Secondly, second principle, reduce opposing variables to an identity. Okay. Okay. An airplane has to have lift to stay up. Okay. Well, the faster it goes, if you have an efficient wingspan, the faster it goes, the more lift it generates. Okay. But the faster it goes, it also creates drag. Okay. And it's hard to push this thing through the air. Okay. So lift and drag are opposites. Okay. But they can cancel each other out. So if you know one, you can use another. So I'll show you something that they did. They borrowed, remember they were in Kitty Hawk, North Carolina on the beach. They borrowed a fish scale from local fishermen. Okay. And when they were testing their gliders, okay, they said, oh, the more it pushes up, we can measure that on the scale. Okay. But if it's being pushed back, this glider that they were flying it as a kite. Okay. That's a drag. Okay. So we can calculate that. That's a simple triangle. Okay. So we can reduce those. Okay. Another is assessing the importance of each variable. It's really crucial to know which are the important variables. Okay. Okay. Well, one of the things they realized was there's three paths to creating a viable airplane. One is you have to have an engine. Okay. One is you have to have a structure. Okay. And the third is you have to have something that balances. Okay. Well, one of the first experimenters with this was Otto Lilienthal. He was a German Jew who I think he ran a stove. He and his brother ran a stove factory. Okay, he developed a hang glider, and a hang glider, you are hanging under this wing. Okay, but if a big enough gusts come, and the way you balance it is you move your body. Okay, and that changes the wing, but you can only move your body so much. Okay, Lilienthal died. Okay, because he was flying low and a gust came and he crashed and broke his neck. Okay, Samuel Langley, who was the head of the Smithsonian. Okay, he was trying to develop an aircraft. What he focused on was an engine. Okay, well, his engine worked real well, and he tried to launch it off a barge in the Potomac, and he launched it off the barge in the Potomac right into the water. Okay, it was the Wright brothers that realized, wait a minute, we are trying to fly in a chaotic environment. Okay, and so we can't develop a plane that simply self-rights itself. We have to constantly, it's unstable. And so what we need are controls to keep on, to keep it stable. Okay, and that was their path. Okay. Okay, another principle of solving complex scientific problems to reduce that um, very complex um, uh, K interaction. Okay, you can try to hold one variable constant. Okay, hold all but one variable constant. Now you can experiment. Okay, and they did that. What they did to do that was they built a wind tunnel, little tiny wind tunnel. Okay, they were fastidious about it. They would when they were trying it, they wouldn't let anybody go near it. Okay, so another way to solve these problems is hold everything constant, and then manipulate one thing, and then you can see what happens. Okay. Okay, next one is separate the variables into relevant groups, and I've already talked about that. Okay, Langley, nobody else could get an airplane to fly because they didn't have the insight of the Wright brothers that it's the control. If you get an airplane that can be stable, then you can add an engine. And in fact, that's what they did. They basically built a glider, and then they had one of their mechanics in their bike shop, because they were bike people. Okay, they got that person to just build an engine. All right, and now they had an airplane. Okay, so the problem is, if there are three basic ways to build an airplane, one is stability, the other is power, the other is kind of lift. It has to do with, you have to have a wing that is the right shape. Okay, well, if you start with power, you're going to crash. If you start with lift and you don't have any stability or balance, you're going to crash. Okay, so you have to start at the right spot. Okay, with any scientific problem. The last one is intuition, and I can't tell you much about that, other than one of the problems that when they were trying to fly their airplane, it had a fixed rudder in the back. Okay, it didn't have, this thing has a little thing that will move back and forth. Okay, and what kept on happening, they'd be flying along, they try to turn. You turn by banking an airplane, and then it would all of a sudden lose lift on one wing and go, okay, and it would crash. They basically, one night, Orville got up, and when he was half asleep, he said, "Oh, so we have too much lift on one wing and not enough lift on the other, so we need to add drag." Well, that seems why would you add drag to an airplane? Well, that was when they developed a movable rudder. And basically, by adding drag, they could balance everything out. So those are my methods, what I call cognitive reductive principles, because they are the ways in which we go about simplifying a matrix. Okay. So I've given you the examples of the Wright brothers, but it will apply to most situations. Okay, you want to follow. That's the path that you need to follow in terms of cognition. And I think I have run out of all my time, Harry. I wanted to say a little bit about the complexity of human prediction, but I guess I don't have time.